Before we talk about any kind of computer algorithms, let's spend some time to discuss the so-called big O notation or big O analysis. This is some kind of language or some kind of metric that people often use to describe the efficiency or the time complexity um, of any kind of algorithm. And it's actually quite important to understand the big O analysis. For people who are coming from the computer language, from the computer science community, this kind of big O analysis seems to be quite simple, right? And it's kind of very natural for people with kind of systematic computer science training. But for people who are sort of not training computer science, it takes some time to actually get used to the so-called big O analysis. It's not really a very difficult concept, but it takes some getting used to. And it's also very important because if you are interviewing for a kind of a programmer job or software engineering job, your interviewer are going to ask you is going to ask you it's going to ask you to describe the complexity of your algorithm, and you have to use the big O language to describe it. Without this kind of capability, it's going to hurt your performance. Right? It's not just your performance in the interview, but also the performance of your algorithm. Right? You need to understand the big O analysis quite thoroughly. In order to write very efficient computer algorithms, right? So how do we actually understand the big O language, right? The big O analysis. Let's look at one example. Example. Here we are just talking about the time complexity of a specific algorithm, right? So when we are talking about big O analysis, there are time complexity and also the so-called space complexity. Time complexity mainly deals with the runtime of a particular algorithm, right? So everything else being equal, you're running on the same kind of computer, you are using the same amount of electricity, and all the CPU and all the hardware is kind of identical, right? So if you compare different algorithms, how long it's going to take to actually finish running a particular algorithm, that's called a time complexity. And when we do this kind of time complexity analysis, what people cares about is not the exact amount of time, the exact amount of microseconds or nanoseconds it's going to take to finish a particular program. People cares about the dependence of the runtime upon the size of the problem. So if the problem size is kind of very large, it's going to take a longer time to run, right? So that's something that's taken for granted. But what's going to be the dependence? Is it going to depend linearly upon the size of the program, or depending upon the size of the problem quadratically or cubically or exponentially? Or that's what people cares about, right? So let's look at this particular example, right? Suppose we're trying to actually move a bunch of people, a number of people, say n people, right? This n could be like a 100, could be like a 2, right? It depends upon this. So n is basically the size of the problem, right? So we're trying to move this many people, n people, from this location to this location, and then the distance between these two locations is 25 miles, suppose, right? And then we have two algorithms. One algorithm is to move this bunch of people with a sports car with 2 seats, but it can drive at 100 miles per hour. Right? The 2 seats, one seat is occupied by the driver. So in order to move this many people, you have to do that one people at a time, right? Because the driver occupies 1 seat, so your capacity for actually moving your passenger capacity is just 1 seat, right? So you have to sort of go back and forth many times. If n is actually big, then you have to go back and forth between these 2 points, 2 locations multiple times. And then the other algorithm is to move a bunch of people with a bus. Let's suppose this bus has an infinite number of seats, right? We'll talk in practice that's not possible, right? But let's suppose that we have this kind of a bus. It's a kind of imaginary bus with an infinite number of seats, right? Later on, when we talk about space complexity, we can actually make the size of the bus, the number of seats in a bus, kind of a finite, and then we can talk about how to analyze the space complexity, right? But let's for now, when we're talking about time complexity, let's just suppose this bus has an infinite number of seats, right? But because it's a bus, so you cannot expect a bus to run at 100 miles per hour, right? Let's suppose it runs at 5 miles per hour, 50 miles per hour, 50 miles per hour, right? So because it has an infinite number of seats, so no matter how big n actually is, right? So any number of people can be fit into this particular bus, right? So you don't have to sort of go back and forth anymore. So all you have to do is to do like one run, right? You can just move this many people, put those many people into the bus, and then drive from this location to this location for like once, right? So let's look at what's going to be the time complexity, how long it's going to take for this sports car, two-seat sports car, to move this many people, right? So it's 25 miles, right? But you have to sort of, every time you move one people, you have to sort of go back and forth, like do one round trip. That's like 50 miles, right? So 50 miles, it takes how long to let's neglect all the time that's for loading the people and then sort of dropping off the passenger, right? So that's going to be like 0.5 hours to move like one person, right? So suppose you have n people, that's like 0.5 times n hours, right? That's this many hours it's going to take for the sports car to move n people from this location to this location, right? And then for the other comparing algorithm, it runs a lot slower, right? 50 miles per hour, right? But you can fit all the people into the bus, right? Let's neglect the time for loading the people, right? And then dropping off the people, right? That's 50 miles per hour, and then 25 miles distance. 25 divided by 50, that's like 0.5 hours, right? So you can sort of see the kind of dependency is very different, right? For this algorithm that's using a sports car, the amount of time actually depends upon the number of people. N, you have an n dependence, right? But here it's a constant amount. It's a constant amount of time. It doesn't depend upon the size of the problem. It doesn't depend upon the number of people, right? And in this case, we call these two algorithms, this sports car algorithm, we call it capital O with a parenthesis with an n inside of it, right? And then we call this particular algorithm capital O with a parenthesis and then with the number 1 in it, right? So maybe you are also kind of confused, right? The time is 0.5 n. Why do you write O n, right? Why not write O 0.5 n, right? The truth is that when we use the big O notation, we usually neglect the constant. We have to drop the constant, right? So whatever the constant is used for multiplying on this size of the problem, you have to drop it, right? And then this you can think of 0.5 hours as 0.5 times 1, right? It's constant times 1. So you drop the 0.5, the constant 0.5. You just write it as O n. And then people just call this kind of dependence a constant time. And then this kind of dependence called linear time, right? So that's some of the conventions that people actually use, right? The thing is that why people want to drop the constants, right? Why people want to drop the constants? It is actually possible for a problem for an algorithm with constant time, like this kind of O1 dependence, to run slower than this kind of linear dependence, depending upon what n actually is, right? Suppose n actually is 1, right? Then n 1 times 0.5 is 0.5 hours, right? That's exactly the same amount of time, right? And in practice, there could be situations where O(n) dependence actually runs faster than O1 dependence, right? But the problem is that if the size of the problem keeps increasing, suppose n increases from like 1 to like 2 to like 3. As you increase n, eventually this O1 algorithm is going to run faster than On, right? And people don't really care about those special cases where n could be very small, right? People care about situations where n could be very, very large, right? So if you write a 0.5 n, looks like very accurate, right? But it just causes confusion because people don't really care about the situations where n could be very small, right? People care about the situations where n could be very large, right? In the case where n is very large, O1 algorithm is always faster than On algorithm, right? And these are two kind of situations, right? Two kinds of situations. And in practice, you could have algorithms that has this kind of a dependence that goes from like a so this is the graph that I grabbed from the web. So the horizontal axis is the input size n, right? And then it's plotting on a logarithmic scale. It's not really linear scale, right? And or is it linear? Okay, so maybe it's linear scale, but the markers uh, are kind of on the power of 2. So the numbers are marked on the power of 2. Oh, it's linear scale because this n dependence, this On dependence, this linear dependence does look like a straight line, right? So this is actually linear scale. So the horizontal axis is the size of the problem. In our case, we can think of it as the number of people that we are trying to move, right? And then the vertical axis is the total amount of time, runtime, of your algorithm, right? So for a constant time algorithm, it doesn't have a dependence on the size of the problem. So it's just going to be a constant. You can think of it like a horizontal straight line, right? And then for linear dependence, On, it's going to be this straight line, right? And then later on, when we talk about more and more algorithms, we're going to see more time complexity. One of them is log n, right? Log n, that's this line. It's better than the linear dependence, right? Because if you look at a fixed input size, say 16, the runtime for a log n algorithm is like a substantially smaller than the runtime for a linear scale, linear algorithm, linear time algorithm, right? And then you could have problems that's kind of algorithm that has this kind of n log n dependence, right? It's worse than linear. It's worse than the linear, but it's kind of better than this kind of quadratic dependence, n squared, right? And then n squared log n, and then n cube. And then in practice, you also have those kind of exponential dependence, that kind of thing. And then also have a power dependence, right? So O 2 to the power of n. And then O x to the power of 2, that kind of thing. N to the power of 2, right? N to the power of 2, that's a quadratic dependence. And then you may have some kind of even worse dependence that depends upon the factorial of the input size, that kind of thing, right? And it's a big topic, and then we're going to look at more examples to make this kind of a understanding, to make this kind of a analysis more concrete, right? So here we're just looking at a sort of abstract example. Later on, we're going to look at the specific codes and try to understand how to use the big O analysis to understand its time complexity.